The H-bridge, I think, gets its name from what's somewhat of an H shape. If you can see, maybe that's one side of the H, the other side right down the middle. And that's the H shape that is there because it employs 4 SPST switching devices or actions. I mean, these could be literally physical contacts or transistors. You know, a transistor could be here, 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 and here. And the device that you're trying to control is right here. And I just have a motor there for this example. And we can fill in the rest of this circuit to show you how this is going to happen. But the H-bridge is really a circuit configuration that's intended to switch the polarity for whatever device is here. So let's fill in the rest of the circuit. We'll show you how this works. I've added a voltage source here, and I think you can see if I want a certain polarity, I can control that with these switches. Remember, these are all individual switches, but if I want, for example, to apply that polarity to the motor, I think you can see, close that switch, right? And we'll get the positive down through that switch connected to the motor terminal. And at the same time, I need to close this switch. And I have now the negative terminal connected to this side of the motor. If I want the opposite polarity, which is what an H-bridge is all about, being able to change polarities for a motor or for anything, really, that needs polarity reversal. A lot of times it is a motor, maybe. I think you can see now just the opposite, of course, the negative side of the power supply. I'll get that to this side of the motor by closing this, and I will get the positive side of the voltage source connected through that contact. And again, could be a contact, a physical contact, could be a relay contact, could be a toggle switch contact, could be a transistor controlled by a microcontroller. One very important thing is obviously the switching must be controlled very carefully. These two switch, or these two, but never these two, right? You'll get a dead short. If you ever have this contact and this contact, or this transistor and this transistor connected at the same time, obviously you get a dead short. If you're using transistors, it is tricky to get, sometimes to get, for example, if you're switching polarity, to get this transistor off before this transistor turns on and actually not have any split second where they would both be on for a fraction of a second. It can happen that they're on for a brief second, split timing, and then you get what's called shoot through, which is current running down through the transistor. So it can be a little tricky with the transistor thing. If you give it one command and one has to go off at the same time one comes on, you have to watch out for that. In fact, some H-bridges designed with transistors, they'll have to work around that. There has to be an off time to allow the transistor that's turning off to turn off. So I mean, to switch, you don't necessarily turn one off and one on at the exact same moment. They'll both be off for a split second, and then the other one turns on. So to avoid shoot through. We found that out the hard way in lab. We were working with some H-bridges and we were blowing them up. We did not allow the 20 milliseconds or whatever was required of off time before reversing direction. So it's a real thing. Another thing to mention is it's basically the same functionality even if the motor and the source were to exchange places. In other words, I can put the source here, put the motor over here, and we'll do that, and we'll show you functions the same. So there's actually, even though the drawing doesn't make it real obvious to your eyes, there is a symmetry here. So let's do that. I'll show that to you. So here I've changed places. Now the motor's over here and the voltage source is here. And I think you can see it still works, right? I mean, if I close these two contacts, well, there goes the positive to that side of the motor, and this connects the negative to this side. Likewise, if I would connect the green contacts, this green contact will take the positive to this side of the motor. And this green contact will take the negative to that side of the motor. So it works. Swapping positions, it still works. One of the simple first exercises that we'll do in lab is to just implement this with an industrial switch. And the easiest way is probably just to take 4 normally open contacts and attach them to an actuator. One thing I might mention, I say we need 4 normally open contacts. You can see that. They are color-coded green, so don't let that confuse you. The drawing I did was just to differentiate between the sets of contacts. But the red circle, don't let that get stuck in your head and reach for red contacts, because the standard, when you get to industrial switches, the red contacts are normally closed. So they're just a little heads up. I mean, it's something I've seen in the past. So that's not green contacts. Those aren't red contacts. They'll all be green contacts when you're attaching them to your industrial switch. But yeah, it's an easy way to implement a forward and reverse scheme for a motor. The other thing about our industrial switch, when we do this simple version, it'll have a center off position, so you can throw the switch, the motor can be forward, reverse, or off. So, but that'll be one of the first easy little things we do. It also helps us get used to what the industrial switches look like, how do you connect the contacts to them and things like that. This same type of switching action can be implemented with a double pole, double throw switch. Here I have one drawn with a center off position. That way it's very much the same. It can accomplish the same thing as this H bridge. And it is essentially the same thing. I mean, do you see we've got 4 normally open contacts, right? Here's one, here's one, here's one, here's one. These are my 2 poles. They move together, right? That's the dotted line showing that the 2 poles of the switch. So it's a double pole, move together, so the double pole and then a double throw. So if you need to remember how this all gets wired or how it happens, or you just need to draw it, from memory, I find it easy to just draw my source, draw my switch, and then here, for example, I used a motor again, but here's the device that I need to reverse polarity on. And I think it's easy enough just to take it one situation at a time. So if you try to think of the whole thing at once, it might get a little confusing. But I can think in terms of, what do I want to do? Maybe I want to bring positive to this side. I mean, I know this is what I want, right? I mean, so lots of times, just like solving any problem, go ahead and map out what you're trying to do, right? And then I think you'll see how to do it once it's clear that what you're trying to do. So you can probably see, well, I do need, in one case, when the switch is in one position, so I'll pick the up position. So when the pole is in the up position, the positive will be here, right? Because this will be connected when the pole is up. Likewise, these poles move together, so this pole will be up, and the negative, will be connected here, right? So I mean, start one scenario at a time. I mean, I think you can see when the switch is thrown here to the upward position, the motor has this polarity, right? Then I just have to solve the puzzle for when the switch is thrown in the down position. I need to take the positive I guess, to this side of the motor. So that's, I guess, easily done, right? The positive, when the switch is down, has to go to this side of the motor. I could just do it like that, right? I mean, there's different ways you could clean up the drawing later. Remember, it's going down. And the negative side in the down position has to come all the way over to this side. So let's take it over there. Yep. And again, you can always rearrange your wires if it didn't work out real nice. This is sort of, all the wires are sort of out of each other's way. So there'd be other ways to draw it, but that one's not too bad. And then look at it. But, you know, here again, I wouldn't try to memorize that exact drawing. I didn't have that in my head. I just kind of figured it out one scenario at a time. It is important to have a drawing, though, in the end. Like we always emphasize, don't try to pick up, you know, the wire and the strippers and the screwdriver and all the tools to wire it. Don't do that while trying to hold on to an image in your head. It's best to do everything in these steps. First, you figure out what you want to do, sketch it out, then take a step back, look at your sketch. Make sure that the sketch works, you know. Make sure as you look at it, you can see the different actions for the switch, the different scenarios. Make sure they all work out, that you didn't cause a short somewhere, and then follow the wiring that you've drawn when you're actually doing the wiring. So you'll hear me repeat that a lot. Never try to wire something up without having a good drawing to look at. You're stretching yourself thin there. Of course you can do it, but use a good chance of making a mistake. And really the next step after you have a good drawing is to even, you know, put numbers on the different connection points, and you'll see that done, so that you really don't have to think through any of the theory when you're doing the actual wiring. You want to avoid that. You want to just be able to pick up your cup of coffee and your tools and do the wiring, not have to rethink all of the actual theory. So you would have these numbered, you know, this would be like, you know, or a letter. This could be A, B, C, D, E, F, you know, and so on. And you can see exactly that you need to take the negative of the voltage source and connect it to, what did I say? That was A, B, C, D, E, F. Connected it to F, you know, point F. And so you'd have everything defined and everything labeled. That's how it really happens in the real world. You know, that way you can't be constantly going back. It opens up a real possibility of making a mistake, but it also just takes more time that way. It's actually faster to be meticulous with your drawing, and then it really speeds up the wiring time. In fact, that's where the temp worker usually comes in to do the wiring. You know, you're not even maybe doing that at that point. But it does make the wiring go fast if you have everything labeled, and you don't have to constantly think, wait, where was that going again? Of course, you want to avoid that. And again, it doesn't matter. The motor could be here. The voltage source could be here. It works the same. I forget if I mentioned it, but these contacts could be relay contacts. I think I might have said it over here. But again, to get it back in our heads, that could be a DP-DT switch. Could be slide switch, toggle switch with a center off position. It could be a relay also. Now, a relay doesn't have a center position, or the ones we have at least. But it could still be a polarity reversal. You would need other things to add to the circuit so that it doesn't just slam from forward to reverse. I mean, believe it or not, some motors can handle that, but you know, or some devices too. But if you need that off position, you know, you'd have to add some more to it. But yeah, they can be relay contacts as well. I will be doing a separate video on the industrial switches, but while we're in this video, I can show you at least, this would be like what the normally open contacts look like for the industrial switches that we have. There's a little actuator here that gets depressed. Let me push that for you. You attach this to the actuator, whatever it would be. So, I mean, it could be anything. It could be a joystick, could be a lever, it could be a push button. But the actuator is going to push this plunger in. And when that pushes in, then the two terminals, which we see one on this side, one on this side, or right down the front, you can see the screws that you would turn. So you're going to attach, right there is where you attach wires. This is a normally open contact that will connect this point to this point. This screw is to actually do the physical mounting of the contact onto the actuator. So we'll show you all that in another video. I just wanted to bring it in to this video. This is what you would need, 4 of these. Here, 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 and here. And that's, again, to mention, they'll all 4 be green. And I say that because here you see there is the color coding for the industrial contacts that we're using. This is a normally open contact. This is normally closed. So the contact, the 2 terminals here and here are normally connected. And when the plunger gets pressed in, this actuation here, when this happens, these contacts open. So they're normally closed. So we do not want to be using this contact. We will use 4 green ones here, 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 here. It's not 2 red and 2 green. Okay, so I mentioned that before, but there you go. You can actually see that. And our exercise will be with the industrial switch with the contacts that can be mounted onto it. We'll use that. Something else I did want to mention, if you were using a toggle switch, and we won't because it's just a pain to connect to these terminals compared to the other industrial terminals. But now here I have I'll tell you something about the toggle switch. I have one here. I didn't find a center off, so this is just one that's going to go one way or the other. This would be a forward and reverse, but no center off. But I wanted to show you something that's just good to know. It's something you should be able to recognize if you have a toggle switch or even a slide switch that has the terminals on the back in that arrangement. So I'll tell you something about that. Yeah. I guess first of all we better say we wouldn't want to assume that these are the poles. It's a good guess, and in this case it's right. These are the poles. So this pole throws here and here, and this pole throws here and here. And I guess they move together, so both of these poles will throw up to here, and then in the other positions they'll both throw down to here. And I mean, maybe it's not a bad little refresh. Do you remember toggle action? Like when the toggle is in this position, which contacts are connected? Is the pole connected here or is the pole connected here? So the switch is down. I mean, the lever is down. Well, if you guessed that these 2 are connected, you're wrong, even though this is down. But maybe you remembered, and hopefully you did, there is this lever that moves like this. So when this, for a toggle, when this is down, these 2 contacts are connected. And when and similarly, when this is in the opposite position, right? If you can see, it's up. Then these 2 contacts are closed because again, this is the action that happens. And then here. Okay, so maybe hopefully did remember that. All these things just save you time as a technician. I mean, you don't want to assume things, but they let you check a switch a little bit faster because your first guess, if you had, you're not going to leave it at a guess, but your first thing to try is right then when you're checking it. It saves you time. But here, finally, all that to just lead up to the fact that I wanted to tell you, if you actually are implementing with a switch that has these kind of pin configuration, which is the most common, the poles are here and here, you'll just see an X pattern. You'll see just a crisscross. These 2 will be wired together, and these 2 will be wired together. Let me draw that, and then show you what that looks like. So we're going to move away from a schematic to the literal thing that you will see. Maybe you've seen that in a cabinet, but it's a dead giveaway that they're doing polarity reversal if they have sort of the crisscrossed, the throws are like sort of X'd, like this throw and this throw are connected together, this throw and this throw are connected together. That's a dead giveaway. And again, it's just a little trick to let you in on. It saves you time. You can recognize what's happening with that switch pretty quickly. Yeah, I'll draw that literal sort of thing on the board here. So here I've drawn or tried to draw the representation of the back view of this toggle switch. So I've got my two poles. This pole throws here and here. This pole throws here and here. And this is exactly the wiring. I put the wiring in blue just to have it stand out. But, you know, this is what that crisscrossing, that X that I was talking about, you know, this throw ties to this one and this throw ties to this one. They're not connected. There's no connection here. There's no node there. And you can put, you know, your source on the poles, and the motor can get connected to the throw points. Again, though, we could switch that. It wouldn't matter. I could put the source here and the motor here, and it would work the same. So these are essentially all the same thing, as is really the point of this video, or one of the points. All the different ways you might run into this same sort of switching configuration. I mean, if I had a relay, I could drop it on there too. So, but you know, a mechanical switch, a relay, contacts, transistors, all are in the game. And speaking of transistors, I do have some examples here of what, you know, a circuit that employs an H-bridge might look like if it's all solid state. I mean, it's definitely true. You can have discrete transistors. You can have power transistors sitting here. That's possible. These examples I have are you know, a little bit more on the smaller side. But they, I mean, this is like the, let's see, what is this? The L298 is a pretty common IC. It's a dual H-bridge. Then it also has other features. I mean, there's digital logic built in, like you would have seen in your very first semester. I mean, just simple AND logic and things like that. It's all intended to bring sort of, maybe at the core it has this H-bridge functionality, but it has a lot of versatility. You can get the job done with like a single bit. You know, if the bit's high or the bit's low, you'll have the H-bridge switched one way or the other, for example, perhaps. You can use this not just to control direction of a motor, but you also build in would be maybe an enable, where all of the contacts switch off, the transistors are off. And then if you think about it, you can use that enable, you can use pulse width modulation on the enable to control the speed of the motor. So that's the kind of stuff, the functionality that you would see start to build into some of these, you know, full motor control type ICs, or whatever they're controlling. But a lot of times it's maybe speed and direction can be controlled, and it's the same. I mean, for stepper motors too. We'll get into that. That's a whole different type of control. But again, it falls down to maybe these ICs can do that as well because of the switching. I mean, if you have 4 poles in a motor and you're trying to switch a sequence, or in some stepper motors, there's just 2 coils, but the sequencing is 1 coil and then reverse polarity on that coil, then the next coil, then reverse polarity on that coil. So you can see down the road we'll be getting into maybe some of those things. And I mean, I'm a little ahead of the game here mentioning it, but they're very versatile. The H-bridge, you know, speed and direction for several different types of motors all comes into play. And some of the extra chips, I think, let's see, I'm guessing in this example here, that would be your dual H-bridge. I can see just because it's got some heavy duty current capability. Some of the surrounding chips then add some what I was saying about the digital logic. just so that you can control with a minimum amount of bits, and you can also make it impossible for like these two transistors to be on at the same time, for example. So there's some built-in simple gate logic that is important to protect from bad things happening. So we'll look at that. I mean, I have these schematics. I have the schematic for this board. I have the schematic for this board. Have the data sheet for this IC. And yeah, I'll publish those for you. They are fun to look at because it takes you right back to, you know, transistors and gates and really basic stuff from the first year, but it's a good exercise for you to look at those drawings and trace the circuit and see what's there and see exactly, you know, what the whole plan of action is. And it's kind of fun to do. It's not a terribly difficult thing to do, but it takes a little time, and it's fun to map it out and be successful at seeing exactly what's going on with these types of little controllers. These will be very practical too. I mean, this is exactly the thing you would need if you wanted, I don't know, a microcontroller like the Arduino, if you're playing around with one of those, or even the microcontrollers that you'll be doing in your programming class. You know, if you want to get them to do something in the real world, obviously they have little bits that they can make go high and low and not drive anything. But those bits would be the thing that comes in to control the transistor switching action that controls maybe a motor or anything else. So yeah, these are common little next step out of your microcontroller. You got to hit something like this and then maybe to a motor. So okay. In this course, our emphasis is definitely more on the industrial side. My intent is to really show you industrial controls and some basic control circuits that are really common. So I don't know that we will, you know, be diving into these boards, exactly these. Although, having said that, I do have them. So, I mean, if you want to play around with them, if you have extra time, I guess is what I'm saying. It's more goes into that category. But yeah, you're welcome to maybe dive into something like this a little bit on your own. These are not what I would call industrial. They're more, you know, a little bit more in the hobbyist realm. But I mean, they happen. It's just we wouldn't be necessarily down at this level. But I mean, I don't want to talk you into it or out of it. Just saying, for my course, we'll probably be on the more industrial controls end, and not really have time. I do have the schematics. It's fun, and it's fun to look at them. One word of caution, and I'll remind you again if you do want to fool around with one a little bit. The fooling around would definitely mean really get to understand it. Don't, as always, don't trial and error. They burn up quickly. This is the one we burned up a few because we didn't read the fine print on the 20 milliseconds between changing a bit value, and there was shoot through that took out the chip. So all those things, just to, of course, you know, don't try stuff, just learn it, know what you're doing, and then implement it. That's how we need to fool with that. All right.